Okay, so welcome back to another video. So in today's video we have this equality proof. So prove the following: s divided by s minus 1 minus s multiplied by the integral from 1 to infinity of the fractional of x multiplied by x to the power negative s minus 1 dx is equal to the Riemann-Zeta function at s. So I should also note that we're also, because we are showing that this equality is the Riemann-Zeta function itself from the expression, it's also good to note that the variable s is in the complex world, but also note that the real part of s is strictly greater than 1. Okay. And we'll also have the fractional of x. So we know that by definition that's actually just equal to x minus the floor of x, which I've covered in several videos back then. So you guys pretty much got the gist of it from that at this point. So it's not really that difficult from my first glance personally, but like to you guys, just once you see the work here, it's actually going to come down very nice, that we're going to get the exact result that we are achieving to obtain. So with that, let's actually just jump right in and start off by just focusing on the expression s multiplied by the integral of the whole thing, of our integrand. So this means well, first let me just establish by saying focus on s, and then with our integral, fractional of x, then x to the power negative s minus 1 dx. And to do this, because we have the fractional of x, so what we want to do is state that for any n that's in the integers, we can actually convert the above integral rather. And then we can actually convert this into a sum of integrals. Yes, I said that plural. Sum of integrals over the interval n to n plus 1, and being half closed and or half open. Simply because the way we're taking this, we want to take we want to take the sum of finitely many integrals as we start from 1 and then all the way up to infinity. So when we do this, we actually get the following. So this is just s, then multiplied with our integral from n to n plus 1 of our sum, our infinite sum, and then start from n is equal to 1 of the fractional of x, and then x to the power negative s minus 1 dx. Alright, now we want to note that on the interval n to n plus 1, we want to notice that obviously, because we have the fractional of, here, let me put this over here, that the fractional of x is equal to x minus the floor of x. Okay, so when we see that we're taking the integral from n to n plus 1, we want to see that the floor of x is actually just equal to n. Okay, good. So using that standard definition, we can say that now the fractional of x, which I said was x minus the floor of x, can now be rewritten as x minus n. So what this means is I can replace the fractional of x with x minus n. And also, because due to convergence, I can actually just drag our sum outside of the integral. So we have that this is s, and then our infinite sum from n is equal to 1 to infinity of our integral from n to n plus 1 of well, simply what I'm doing, I'm just restating what I said from the original, and now we can convert this as s and then the infinite sum of our integral from n to n plus 1 of x minus n, and then I can actually just move this to the denominator since I factor out a negative here, so this is negative, and then s plus 1 quantity. So using the rules of exponents, I can actually just move that to the denominator, so we get s, or x to the power s plus 1 dx. Okay, but we can actually clean this up just a little bit. So meaning I can actually write this into two fractions. So we get this is, so everything just like before, the integral n to n plus 1. However, this time I get that because they both share the same base of x, so one of the x's cancel, so that means I'm left with just 1 divided by x to the power s, and then subtract that with n divided by x to the power s plus 1 dx. Now we can actually just compute this definite integral, which that's just a piece of cake, because we're taking everything in respect to x, and that's not that difficult to show. So let me just rewrite everything from before equals 1. Then now computing this definite integral, you'll see that we have, let's see, so it's plus 1, simply just x to the negative s plus 1, then divide by that, so it's just x minus s plus 1, then divided by negative s plus 1, and then subtract that from over here, so it's minus this and minus and plus 1, then the 1 cancels, then we just get n times x to the power negative s divided by negative s, and then we evaluate this from our bounds n plus 1 to n. Now next thing obviously is to evaluate our bounds, and I'm actually going to take just a bit of a shortcut. What I mean was that we evaluate n plus 1 for here and then subtract that with the evaluated bounds at n, but I'm just actually gonna rearrange some terms a bit so that way it's it'll come down nice without having to do things the long way. So when you after actually doing that rearrangement, you get the following. So you'll get that this is just n plus 1 to the power negative s plus 1, then divided by negative s plus 1. You know, I could factor out the negative, but let's not jump ahead of ourselves. We can save that step for a little later. And then, so it's n times, and then now we have the inside the quantities, n plus 1 to the power negative s, and then minus n to the power negative s, and then divide this by negative s. Cleaning some things up now. Well, not exactly cleaning up. What I'm actually gonna do is I'm actually just gonna distribute the s into our infinite series, and then doing this yields us, so we got this bracket, we get that this is just s then times n plus 1, then to the power negative s plus 1, then subtract that with n to the power negative s plus 1, okay, and then all this is being divided by negative s plus 1, subtract that with s times n, okay, quantity, so n plus 1 negative s, subtract that with n and then to the power negative s, and then we just divide this by negative s. All right, and then let's see, yeah, I think I got one more room for this. Okay, and now cleaning this up, I can actually factor out an s plus 1 from our the left hand of our inside expression. So we get that this is, let's see, so n is equal to 1, and then so I factored the s divided by s minus 1 out from the left. So then this is, let's see, so it's 1 divided by n to the power s minus 1. Subtract that with, so we have quantity n plus 1 to the power s minus 1, okay, and then add this with n divided by n plus 1 to the power s, and then subtract that with 1 divided by n to the power s minus 1. Okay, good. So far so good. Now, now as you can see, we have to clearly evaluate these terms here. But to do this, we're gonna actually have to evaluate this one by one. So how about I label this as the following? So this one's going to be S2, and then this is going to be S1. I hope y'all can see that. Can you see that? Yes, you can, just barely. Okay, good. I apologize for that. I know I should probably zoom out just a little bit, but we'll kind of get a little close, so it's okay. All right, so moving forward, now let's actually note some things. So what we want to achieve is we want to achieve that the left-hand expression is equal to the Riemann-Zeta function. Well, let's actually do that. Let's do that in a way where we can actually get the Riemann-Zeta function. But first, let's actually note the following. Let me actually use orange for this. Note that our Riemann-Zeta function S is actually equal to the infinite sum, starting from n is equal to 1, of 1 divided by n to the power s. Okay, so let's also note that s minus 1 is actually just equal to the same thing except the exponent's s minus 1. Now let's pay attention. Let's actually focus on this term for just a second. You see where I'm pointing? It's what we're focusing on. We're focusing on 1 divided by quantity n plus 1 to the power s minus 1. Okay, so let's write that out. So we have 1 divided by quantity n plus 1 to the power s minus 1. Simply, it's just equal to the same thing, s minus 1, and then subtract that with 1. As you can see that if I were to expand this series out, if I start with n is equal to 1, we get that this is just 1 divided by 2 to the power s minus 1. So rather, the index starts at 2 over here, but we have to evaluate what the index is when n is equal to 1. So when we do this, it's just 1. It's basically just subtracting one of the terms from here. So that's how we come down to this conclusion. Okay, but anyway, enough of that. We already got what we need, so we can actually evaluate our S1 first. Let me write the following. So S1 is equal to, so let's see, we have S divided by S minus 1, and then in our parentheses, this is, let's see, n to the power S minus 1 minus n plus 1 to the power s minus 1. Now, that's simply just equal to, so we have outside just s divided by s minus 1 so far. And now we just substitute. So this is just the Riemann-Zeta s minus 1, and then subtract that with what we have, 1 divided by n plus 1 to the power s minus 1, which is here, the Riemann-Zeta s minus 1. Then distribute the negative, we get a plus 1. And so simply we just get that it's just s divided by s minus 1. Okay, cool. Let me just evaluate this in black. So we have, or underline, so we have s1 is equal to s divided by s minus 1. So now the next thing we need to evaluate is our s2 over here. S2 is equal to n divided by n plus 1 to the power s, and then subtract that with 1 divided by n to the power s minus 1. Tell you what, let me actually write the sum out so we know what we're working with. Okay, so we have this. Now, what I want to do is let's actually add and subtract a 1. We're only focusing on just the left, so we're going to add and subtract a 1. So we get the following. So I'm just writing the same series expansion. So this is what, n plus 1 and then minus 1, then divided by n plus 1 to the power s. Subtract that with 1 divided by n to the power s minus 1. And we can actually separate this out into 3 sums. So we have this infinite series, n is equal to 1 of, now they share the same base. So what I can do is I can actually just drag that to the bottom. So we get that this is, there should be an s minus 1 in the denominator. So this is 1, and then n plus 1 to the power s minus 1. Okay, and then subtract that with our, let me actually write a bracket just to indicate. So let's see, just this. Okay, and then what I said was 1 divided by n plus 1, then s minus 1. Okay, and I'll subtract that with 1 divided by, that's coming from over here. So this will be n plus 1 to the power s. And then I'll subtract that from over here. So it's 1 divided by n to the power s minus 1. We already established just from our facts about the Riemann-Zeta function with its, what is the definition. So we can just replace some things from here. So as defined as to follow. So we get that this is, let's see, we have Riemann-Zeta s minus 1 minus 1, okay? And then over here, this is just, and then over here is, we still just get the same sum series, but let me save that for the last term. And then over here, which is fine because this is just it's commutativity. And over here we have 1 divided by n to the power s minus 1. That's also the Riemann-Zeta function at s minus 1. And I'll subtract that with our series over here of, 1 divided by n plus 1 to the power s. Now, if we simplify this out, the Riemann-Zeta of s minus 1, they cancel, so we're left with minus 1, then minus our infinite sum, and 1 divided by n plus 1 to the power s. Now, we can actually simplify this out even further because notice that if I were to, we're gonna, basically what I'm getting at is we're actually gonna change our index and this will manipulate the left hand side of this equation. So when let's say if I were to evaluate this term at n equals 0, so we get that this is 1 divided by 0 plus 1 to the s, which is 1, and that's a negative out to the side. So really, I can actually write this as a negative multiplied by the infinite sum, but our index will have to start at n equals 0 of, and then it's the same series. So it's n plus 1 and then to the power s. And then you'll see that this is actually just equal to, changing the index again a second time, you'll see that this is actually just the negative Riemann-Zeta at s. So there we have it. That's our S2. So concludes that this is equal to S2. So now next we have to do is just combine our S1 and S2 together. So to reestablish, let me just go back to the red. To reestablish, so S1 plus S2, and that's coming from over here. We take the infinite sum, which we already did. So we have that this is S divided by S minus 1, and then plus the negative Riemann-Zeta of S. Okay, cool. So let me just underline this in black again. And that just concludes evaluating this integral. Also, I should probably just write that that's equal to the integral on this side. So that's equal to, let's see, it's s multiplied by the integral 1 to infinity of the fractional of x, and then multiplied by x to the power negative s minus 1 dx. So now with that, now we can actually just go back to the original integral. So therefore, that means we write s divided by s minus 1, then subtract that with s multiplied with the integral from 1 to infinity of the fractional of x multiplied by x to the power negative s minus 1 dx is the same thing. Simply that's just s divided by s minus 1. And then subtract that from what we showed over here. So this is s divided by s minus 1. And then distribute the negative so we get a positive Riemann-Zeta function of s. And we come to the conclusion that this is just equal to the Riemann-Zeta of s, like so. And there we have it, underlined in this red box. All right, that's pretty cool if you ask me.